Tommaso, do you see recording? Everything is okay?
Yes, everything looks good. All right.
Okay, so you can start and we will stop. So again, if you have question, maybe write first on the chat and then we will Dennis will let you either mm, talk or either he will do the question for you. Thank you very much.
All
Thank
right.
you, Tommaso.
Thank you, Alberto, and thank you, Dennis. Thank you, Marcus, Fabien, and Nicolas for the kind invitation, and most of all for staying the course through these hard times and keeping the school alive and actually setting up a terrifically collaborative environment around it. So it feels almost like being in Les Houches. It's a best approximation. All right, so actually, as much as I would like to be in Les Houches at the moment, well, I can claim that even though I'm not the closest person to it, probably people in Grenoble are closer. I'm probably one of the few privileged ones that can see Mont Blanc from his window. And these are, what you see here are pictures of the Mont Blanc taken over the years. In different moments of the day. So, all right. So it's a very reassuring view to know that it's always there. Okay. So today I'd like to discuss how to probe excitations using non-equilibrium quantum matter, so using quantum quenches. And the goal of the lecture the goals of the lecture really is to try and keep it as simple as possible, trying to give you through the example of quench dynamics, some simple instances of quantum many-body non-equilibrium physics and simple techniques, quote unquote, at least conceptually simple, to study quantum many-body dynamics. And also hinting the connection to experiments, current experiments on quantum simulators. Okay, and in the spirit of maximum simplicity, I'd like to get as many messages across as possible. So please do interrupt me at any moment in time. You can post a question in the chat or just really unmute yourself and interrupt me, even if I cover a part of the material that I prepared. Is not an issue at all. Okay. All right, so let me start from what this lecture is not going to be about. So it's typical. So it's not going to be about equilibrium quantum matter and in its excitations, which is nonetheless the historical framework in which people have studied excitations of quantum many-body systems. So let's say let's start by agreeing on what quantum matter is. So probably everybody has, among you has their own opinion about it. So in general, I would say it's systems whose macroscopic behavior is governed by quantum mechanics, so at least at low enough temperatures, things of superconductors, superfluids, quantum Hall fluids, frustrated magnets, and so on. And all of these systems have typically the common feature of having an exotic, somewhat ground state, and low energy excitations that are also very interesting, often exotic as well. Actually, most of the exotic aspects will be lost in my lectures, as I will try to make the point that you don't need too much exotic physics to have interesting non-equilibrium dynamics. But anyway, so when you look at equilibrium studies of quantum matter and its excitations, typically what people try and do is to get as close as possible to the ground state. That is, typically taking a quantum material, so a solid state realization of quantum matter. You would stick it into a fridge, a dilution helium fridge, for instance, in such a way as to get as close as possible to T equals 0, and then reconstruct the low temperature phase diagram of the system. And then once you know how to prepare your system at low enough temperature, only then do you study the excitations. And typically that's done within the linear response paradigm. So that means you have your system at equilibrium, coupled to a heat bath at all times, and then you probe it by shining some probe on it, for instance, scattering neutrons away from it, something that's, it's a common sport in Grenoble, for instance. And then you just record the energy, resonant energy momentum transfer to the system by looking at how neutrons are scattered from your material. And this gives information about the dispersion relation of excitations that are dumped into the system when a neutron is scattered, okay? And so the main information that you retrieve from this is the dispersion relation of quasi-particles. Okay. So that's more or less the traditional framework, and the framework in which I work instead, it's rather different, and it's trying to probe similar excitations, but in a completely non-equilibrium setting. And the idea is that really the inspiration for this work comes from synthetic so-called quantum matter, namely quantum simulators. That's probably the more common name these days, based on atomic physics, called atoms or trapped ions, or nanostructure systems like superconducting circuits. And in these systems, there is no environment, essentially by design. So you try and decouple these systems as much as possible from any environment. And hence, it's typically rather difficult to prepare them in some highly non-trivial, exotic, possibly low energy state. Typically, the simplest way of preparing them, fiducially at least, is to prepare them in some trivial factorized state. It's the initial state, the most naturally prepared in the experiments. It's a factorized state, degree of freedom by degree of freedom of the system. And then you could think that this state in which you prepare your system is actually the ground state of some initial Hamiltonian that you can try and adiabatically transform into an interesting Hamiltonian that features some very important physics. But the adiabatic preparation, it's typically a hard task. It takes quite some time by definition of adiabaticity, and typically experiments don't have so much time to run before the environment actually reappears in the form of parasitic effects that people had tried to eliminate. So adiabatic preparation is not the first option. The first option is actually to let the evolution go and let the initial trivial, quote unquote, state evolve under the full many-body dynamics, performing a so-called quantum quench experiment. And moreover, another feature of these experiments, unlike what you can do in condensed matter, is that you can projectively measure quantities on your system at any arbitrary time. So monitor the time evolution fully. Okay. All right. So how does the dynamics of observables then speak about the nature of excitations in these systems? That's very simply seen by just doing an elementary calculation to consider, again, the quantum quench setting of the evolution of an initial non-stationary state and your eigenstate and the eigenstates of your Hamiltonian expressed like this with eigenvalues En. And then just rewrite the expectation value of an observable, in its time evolution by inserting a couple of resolutions of the identity on the eigenstates, and you get this form that contains three main ingredients. The first one is the overlap of the initial state with the eigenstates of the Hamiltonian. So it tells you what is the excitation content of the initial state. So what excited states the initial state contains. And these states are the ones that are going to appear in the dynamics. The second element is the matrix element of the observable among these states that are selected by the initial state. So this is a property of the observable that you're looking at. And the third element is a phase factor, which is dependent exclusively on the Hamiltonian spectrum, and it's really speaking about the eigenvalues. Okay, so that tells you. So this expression is telling you that essentially the dynamics of A of t is given by. It comes from dephasing dynamics of various components in this sum related to different energy differences among states that are connected by the observable and that are present in the initial state. Another way of seeing this, more pictorial, that I like, is to think of a quantum quench experiment as this kind of experiment where a diver jumps into a pool. So, so the initial state sets more or less like the height of the springboard from which the diver jumps. So the energy, the initial energy of the state, and the pool is like the Hamiltonian that's going to give you the evolution of your system. And when the diver comes into the water, of course, it's a big splash, and the splash in this picture here is really the dephasing dynamics comes from the evolution of the phase factors in front of the various eigenstates of the Hamiltonian. And then what you do is that you choose a particular observable to monitor these dephasing dynamics in such a way as to extract the nature of the excited states of the Hamiltonian. Okay. So that was my initial blah blah. Any question so far? Or doubts? Okay, so if that's not the case, let me then move on to the outline of what I'd like to discuss today. So, so my talk will be, my lecture talk will be mostly focused on what I like to call a gentle quench. So quenches that at low energy that are targeted to indeed reveal the low energy excitations. And in particular, view them from the point of view of quasi-particle excitations. In particular, I'll focus on dynamical manifestations of quasi-particle excitations in the dispersion relation. I plan to talk about also localization effects of quasi-particles, but I think I'm not sure I will be able to cover that part. But otherwise, I'd very much like at the end to go beyond the quasi-particle picture of excitations and discuss something more fundamental, which is the Anderson Tower of states and how it reveals itself in the dynamics. Okay, so let me start from the first subject, which is the general discussion of low energy gentle quantum quenches, and specifically I'll focus on quantum spin models. So, so what quantum spin models will I be talking about? Well, actually, they're going to be very simple quantum spin models, simple in their equilibrium physics, but they are paradigmatic when it comes to experiments in synthetic quantum matter. So, so the two classes of models that we focused on are long-range XX models, that is models involving the interaction of X and Y components with a power law interaction, with the interaction decaying as a power law of the distance, and also transverse field Ising models, also with power law interactions in general. And these models are realized by a plethora of different platforms of quantum simulation, bosonic Mott insulators, Rydberg atoms, trapped ions, also superconducting circuits. Here I put some references. Actually, I was meaning to add a reference on superconducting circuits that I forgot to put that. Maybe I'll put it later and when I share the slides with the organizers. Sorry about that. Okay, so so as you will see, well, these systems have an embarrassingly simple ground state and seemingly simple excitations, but their dynamics is very interesting. And I think that if there is an important message that I'd like to convey, that probably is already known to most of you, is that to have interest in quantum dynamics, you don't need to have a fancy equilibrium dynamics in your system. You can stick with very well-known models for which you think that there's nothing new to be said, and instead there is still new surprises that come along. Okay, so when it comes to discussing the quench dynamics of these systems, say the ground zero level, the entry level for the theoretical treatment would be to do a mean field approximation. That is to approximate your ground state, your evolved state at every time, at every moment in time, as a factorized state in which you attribute a specific state to each spin, which means that each spin is a direction, is a well-defined direction on the block sphere, and so it's parameterized by two angles theta and phi. So that means that the evolution of a mean field state that is assumed to stay mean field along the evolution is just akin to the evolution of classical spins, of classical orientations on the sphere. And in fact, the mean field equations are exactly equivalent to the equations of motion for classical spins, for the classical limit of the models of interest. So there's nothing much quantum about the dynamics here. And also there is no correlations, no entanglement that comes along. And so it feels like a big desert, okay? There is some dynamics, but again, it's not, it doesn't have any special quantum feature. Then to move beyond the mean field, so the first step that you would do is to introduce harmonic corrections to go to linear spin wave theory, okay? And that's going to occupy a big part of the story that I'd like to tell today. So within linear spin wave theory, you give away the assumption of a mean field evolved state, but you still have to keep the mean field approximation somehow in the background, because for the mean field, for the linear spin wave theory to work properly, you need to make sure that the ground state of your Hamiltonian can be described somewhat faithfully within the mean field approximation. When I say faithfully, I mean that the main features of the ground state, such as the existence of order and of long-range order and its nature, the orientation of the order parameter, and so on, should be captured at the level of a mean field. Okay, so if that's the case, then you're in business because what you're going to be with linear spin wave theory, it's just a harmonic approximation around the ground state. And to do this in practice, in the spirit of a school on theory and computation of quantum dynamics, what you have to do is to look at the mean field. To first minimize variationally the Hamiltonian energy on the mean field ansatz. So find the theta and phi angles at each side. They could be uniform, they could be non-uniform. It depends on the kind of model that you're looking at. And then, whatever the configuration that you've got in the mean field, you have to define locally the quantization axis side by side as the axis that is defined by the orientation of the spin in the mean field ground state. Okay, so do a rotation such that the mean field state appears as a trivial ferromagnetic state with all spins aligned along the quantization axis. And then once you've defined this rotation reference state, you introduce a spin boson transformation that maps the spin operators onto bosons. And the bosons, what they express is the deviation of each spin, is the fluctuations of each spin with respect to a configuration in which the spin is perfectly aligned with the local quantization axis. Okay, so the boson population measures the deviations of each spin from its local polarization axis. All right, so this is within Holstein-Primakov transformation. There are other spin boson transformations that one can think of, but I'll stick with a linearized version of spin boson transformations, which essentially makes all transformations equivalent. Okay, and once you have this linearized spin boson transformation that gives rise to a bosonic Hamiltonian, which by the fact that you've chosen carefully the mean field state as a reference to build the spin boson transformation, will only have will have its first non-trivial term as a quadratic one. There's no linear term in the bosonic operators. And then in principle, of course, there are terms beyond quadratic, but you just neglect them. And neglecting them is actually inspired by the idea that for all of the physics that you are interested in, the bosons that are described by this Hamiltonian are supposed to be diluted, to form a diluted gas. So to have a density that's much smaller than the maximum density that you can authorize to stay within the Hilbert space of spins, which is 2s, and it's equal to 1 for spin 1/2 systems. That's the case that I'm going to consider throughout my presentation. Okay. And then once you have a quadratic bosonic Hamiltonian, it's something that we learn in many body classes on quantum many body physics. You just treat it with a Bogoliubov transformation, and that's a linear transformation between bosonic operators, and it's reduced to a diagonal form that reveals the existence of elementary bosonic excitations with a dispersion relation omega of k. Okay. There's a question.
Yes, I was actually wondering if this whole calculation was static.
At the moment, it is. I mean, it's just setting the stage. So it's mapping the Hamiltonian from spins to bosons, and then the dynamics starts. I mean, then I
was wondering if instead one could perform a dynamical spin wave transformation somehow, non-equilibrium spin wave theory.
Absolutely. So absolutely. So that's a great question, and in fact, today I'm going to discuss, let's say, the simplest way of generalizing the old spin wave theory to time-dependent phenomena, but you can do it more generally and have and somehow think of this spin boson transformation as being somewhat time-dependent in that the reference frame, so that this quantization axis actually moves in time, and so in some sense the bosons are defined with respect to an evolving quantization axis. Yes.
Okay, thank you.
Thank you for the question. Any more questions? Okay, so again, as I said, this theory actually is almost, I don't know, 90 years old or something, but it has been revamped in the context of non-equilibrium physics more recently. And here I gave a few references of our work and the work of other people, but just recent ones. I'm sure there's many more, and it's by far an incomplete list. Okay. All right, so then, once you've set the stage of the linearization of the spin model into a quadratic bosonic model, what kind of dynamics can you study? So the dynamics that I'm going to study throughout my presentation is actually very simple, but it has the beauty of being very transparent in some aspects. And that's a dynamics that initializes the state in the mean field ground state. Okay, so the initial state is just this factorized. Let me go back. This factorized state, which is not the ground state of this Hamiltonian, because the ground state of the bosonic Hamiltonian contains actually quantum renormalization of this state. It contains a finite population of B bosons. Whereas this one here is just the vacuum of the Olsztyn-Primakov bosons. It has the advantage, being the vacuum, of making calculations quite simple, because everything you have to calculate in terms of time evolutions is going to be the vacuum acceptation values of some linearly time-evolved observables. And also it has the beauty from the point of view of experiments that it connects with the fiducial states that experiments can initialize, that is factorized states. Also, it has the beauty that it's a very simple state that has no correlations nor entanglement. So anything, in terms of correlations and entanglement that's going to appear in the dynamics comes from the dynamics itself, and it comes from, in fact, non-mean field dynamics because there is no dynamics at the mean field level if you start from the mean field ground state. Okay. Okay, so to have a more microscopic insight of what the dynamics starting from the mean field state is going to be, well, let me just spell out the quadratic Hamiltonian, which has in general this form. So it is not, it's a quadratic bosonic Hamiltonian, but it's not a Hamiltonian of free bosons. It's an Hamiltonian of bosons that hop, but also bosons that are created in pairs. Okay, so it's a Hamiltonian of bosonic quasi-particles, and luckily so, because if the initial state is the vacuum of these bosons. So if you just had bosons hopping around, the vacuum wouldn't evolve. It's a desert; it stays a desert. But then, thanks to the existence of this pairing, these terms that create and destroy pairs on interacting sites, then actually the vacuum, it's populated with quasi-particles that are created in pairs and then can move around and can propagate. Okay, and so the desert starts blossoming. Okay, so this is the point of view of the Holstein-Primakov boson, so how the dynamics is going to proceed. But a different point of view is the one that's given by the other bosons that I've introduced. These are the ones that are related linearly to the B bosons. The beta bosons are the bosons that diagonalize the quadratic Hamiltonian, and whose number instead is conserved, okay, by construction, by definition of Bogoliubov diagonalization. And so, well, the initial state in terms of these bosons doesn't look as simple as the beta bosons. Since their density has to be conserved, well, they need to be there in the first place. Otherwise, there wouldn't be any interesting dynamics. The vacuum would stay the vacuum. So the initial state in terms of the beta bosons has a seemingly complicated structure. So it's actually a state that contains superposition of, between the vacuum and many states in which beta bosons appear in pairs, counter-propagating at opposite wave vectors. This state is called, it's a set of so-called two-mode squeezed states in quantum optics. And if you view it in real space instead of momentum space, so it's a state in which particles, beta particles, have appeared in pairs with some, in some paired states with some wave function, which is the Fourier transform of this coefficient here, Vk over Uk. Okay, so the initial state appears to be rather entangled from this point of view. It contains lots of entangled pairs of quasi-particles, but in fact it's not. It's still the mean field state. So by some magic, the superposition of several entangled states that they make up this state gives rise to a non-entangled state. But then as the dynamics flows and you go through the quench, so what the quench is going to give you is just that these beta operators under the action of the Hamiltonian evolve simply by picking up phase factors. So beta dagger picks up a phase factor e to the I omega kt. And so in this expression here, this sum contains terms that start to dephase. And the effect of dephasing is actually the one of really letting the entanglement emerge. Other way of seeing this is that the beta particles propagate in space and they entangle the system. Okay. All right. So these are, this is the picture as intuitive as I can possibly make it for the dynamics related to spin wave theory. And you have to keep in mind that actually spin wave theory, it has the advantage of being the simplest quantum field theory that you can define and solve to describe the dynamics of your system. But also it has a fundamental limitation. It assumes that the initial state, the mean field state, doesn't evolve very much, because it has, the dilution. Let me go back. The fundamental assumption of dilution of quasi-particles here that allows you to linearize the Hamiltonian amounts to saying that there are very little deviations of the spins with respect to their local quantization axis. So that means that the dynamics is bringing you not very far from the initial state. So you have, sorry, let's go back. So you have gentle ripples around the initial state that appear in the system. And so that means that you assume that the initial classical order that you impose in the system persists in time. And this is true if you apply a field that sustains this order, or if the order is spontaneous, you'd rather take a very large system such that you have spontaneous symmetry breaking that stays true at very long times. And I'll come back to this towards the end of my presentation. But for the moment, I'll give this as a working assumption for the rest of the first part of my presentation. A warning that I should equip you with is that these assumptions may not be true, and spin wave theory may fail you miserably. Okay, so you have to be careful when you use it that these assumptions are correct. They may not be correct at all times. They maybe you can have classical order that decays in time. Then you have to make sure that you're just observing your system over the correct time window. Okay. So, but this said, given that the linear spin wave theory has important limitations, it kind of calls for improvements, and natural improvement that we are working on is to go from linear spin wave theory to non-linear spin wave theory and include the nonlinearities. And this is something you can do rather systematically, but I won't have time to talk about today. And it's the core of the PhD thesis of a recent student that I recently graduated with me, Raphael Menu. And another strategy to go about improving beyond the linearized quantum description of your system is to go for phase space methods. It's a completely independent approach. And for quantum spins, that comes in the flavor of the truncated Wigner approximation in its most recent formulation as a discrete truncated Wigner approximation. It's a very interesting approach. It has its own merits, also its own limits, and we are exploring it at the moment. But I won't discuss this either. What I will discuss instead and show you results about is a third way, which is to use instead the variational approach, which is kind of a Swiss knife in terms of studying quantum many-body systems, and in particular we use it in the flavor of time-dependent variational Monte Carlo. And let me state briefly what this is about. So ideally, you would like to describe the evolution of a state, which for spin 1/2 spins, it's a superposition of to the power n states in the computational basis. Say these are eigenstates of the SZ operators side by side. So you have to track in principle 2 to the power n coefficients in time, and that's of course mission impossible. But what you can do is that you postulate, that these coefficients are in fact known functions that are parametrized with parameters, with a set of parameters A that form a vector, and the evolution of these coefficients is in fact nothing but the evolution of the parameters themselves. And these parameters come in a string of m terms, but m is supposed to scale polynomially with the number of degrees of freedom, not exponentially. And hence, you have a viable approach. Now, throughout the school, you'll see several examples. You have seen already, I'm sure, examples of such a philosophy. So in Mari Carmen's lectures, well, I presume she discusses matrix product states, which is to cast these known functions to postulate, in the form of a trace of a product of matrices. And so this vector of parameters is given by the matrix elements of these matrices here. Okay. In next week's lectures, the ones of Giuseppe Carleo, you'll see actually this presumed known function to be expressed as a neural network where the A's are the connection parameters of the neural network. And there are many more examples, and there's a lot of creativity that's been invested these days in crafting different variational states. The one state that we have used, and that I'll show you results for, is actually, if you wish, in my opinion, the simplest you can think of, that captures correlation effects at all scales. And that's, in this state, the A parameters just express the correlations among pairs of spins. There are coefficients that weigh different configurations for spin pairs. So this ansatz is called different ways. You can call it a pair product state or a spin Jastrow state. We like to call it, for historical reasons, an entangled plaquette state, just because these objects here entangle explicitly pairs of spins. And it's really the minimal, in my opinion, entangled state that can capture any pattern, essentially, of two-point correlations at all length scales. And in the worst case scenario, it depends on a number of parameters that scales quadratically with the number of sides. But typically, if you have symmetries, it just scales linearly. Okay. Right. So, and then how do you treat these states? So you have to evolve them. You need to have a rule on how to evolve them. And the rule to evolve them is also well known, and it universally applies to any state. I mean, there are different strategies, but let's say for generic states that you treat with variational Monte Carlo, this is the general rule by which you express the evolution of the coefficients of the state with a first order differential equations. It's a highly nonlinear one in which the derivative of the parameter vector A is equal to a complicated object that is an expectation value on the evolved state of some operators. And I won't have time to go into the details of how this formula comes about. I probably you'll learn more about this next week in Giuseppe's lectures, or maybe even in Mari Carmen's ones. But the idea behind it is the so-called time-dependent variational principle, and this can be sketched rather easily, I would say. So at every point in time, you have your vector psi of A. And if you evolve it infinitesimally in time with your Hamiltonian, this will become this vector 1 minus I h dt psi of A. And you'd like to approximate this vector as much as you can with a vector which is instead of the form psi of A plus an increment of your variational, of your parameter vector dA. And the vectors of the form psi A plus dA, they lay in a manifold that's called the tangent space. And so these equations, they stem from the attempt of finding the vector psi A plus dA, which is the shadow, if you wish, the projection of the exactly evolved state onto the tangent space. Okay, that's the geometric picture of the time-dependent variational principle. Okay, so I'm done with my part about techniques. So any questions about this? Yes, there's one, please.
Yes, can you hear me? So
Yes.
maybe could you describe a little bit more detail, kind of where the approximation in this ansatz of this pair state is? Because you say that it has entanglement at all length scales, but somewhere there has to be a sacrifice, right? Is there
Of course. Well, yeah,
clear where it is?
Yeah. Well, this is an excellent question and a very hard question to answer. What I can tell you simply is that let's say the most general ansatz in which you build correlations explicitly by in this form with having coefficients that depend on the configurations of 2 spins. Or 3 spins or 4 spins, it would be indeed to go beyond 2 spins. So it would be, generalizing these ansatz would imply to have a product over for instance, trios of spins of coefficients that depends on sigma I, sigma j, sigma k, and then another product that depends on quartets of spins and so on. Okay, so in this way you would be able to capture 3 spin correlations, 4 spin correlations, and so on. And actually, to have a full description of the evolved quantum state, in principle, you need to reproduce correctly the evolution of the reduced density matrix of any subsystem, and the reduced density matrix of a subsystem contains correlation functions at all orders within that subsystem. And thereby you would need to have, in principle here to build explicitly correlations among spins at all orders. But this, of course, is the exponential overhead that you want to avoid. Okay.
But these 2-point correlations, they're not bounded to anything. So there could be strong 2-body correlations, but weak 3-body correlations.
That's okay. So this is the physical intuition that behind the choice of such a state, is that if you're able to describe 2-point correlations correctly, you're probably on a good track, and the rest could be details. But this is, of course, a very optimistic point of view. In fact, in no sense in the minimization, in this time-dependent variational minimization of your state, you are optimizing your state so as to reproduce optimally the 2-point correlation functions as they evolve in time. This picture here is just trying to approximate geometrically your evolved state with the best you can do within these ansatz. Then what this construction gives you in terms of correlations, you don't know. I mean, you may even with this state, which is supposed to capture 2-point correlations very well, you may fail in describing 2-point correlations because these ansatz here want your state to reproduce at best 2-point, 3-point, 4-point correlations, and so on, depending on which ones are important. Okay, so it's in the most general answer I could give to your question, and also to the question, to part of the question that's coming up in the chat, is that having a variational ansatz is generally an uncontrolled approximation unless you have a way to systematically improve the ansatz, which is what for instance, matrix product states give you. But the systematic improvement comes at some point with an exponential cost. So here we're just taking the ansatz as such and let it go and see what kind of physics we get. We could improve it, but first we want to have a sense of what the simple ansatz can give us. So answering to the question of Darwin, can you estimate the error you're making here? How does this technique behave for longer times? Yeah, that's another formidable question. And so the error can be estimated locally in time. So you can know, by this construction, you can estimate how much you are missing of this orange vector by approximating it with the red vector. So then it's very difficult to say at time t how much am I differing from the exact solution at time t, because I don't know it, unless I have a benchmark calculation and gives it to me. So you have a sense of what is the local error in time, But then knowing how this error accumulates is difficult to have a feeling of. Okay. Any more question? All right. So if there's none for the moment, let me keep going. But again, you can stop me, and I can backtrack at any point in time. So so let's look at now some applications of all this after this long introduction. So in particular, how to study the manifestation of quasi-particle excitations in the non-equilibrium dynamics. So as I said at the beginning in discussing linear spin wave theory, so so essentially the linear spin wave theory describes the dynamics of conserved in number beta quasi-particles that dephase in time. And you can imagine then that in the presence of free quasi-particles that propagate with dispersion relation omega k, any signal, any modification of the state will propagate spatially with the maximum velocity that's dictated by the maximum group velocity of these quasi-particles. So there is a bound for the velocity at which signals can propagate in the system that sets then so-called causal structure for correlations or for how correlations develop in time. So in other words, the spin wave theory, or as much as any quasi-particle description of your quantum system, is a perfect setting to understand this general picture of quantum many-body dynamics, which is the so-called light cone effect, which has been put forward by Calabrese and Cardi way back in the day, and discussed by a lot of studies, and even shown to hold experimentally. And the idea is just that if you look at any point in space of your system, so here I'm looking at a one-dimensional system, so around every point in space, correlations build up, or things change around every point in space within a region which is bounded spatially within a causal cone that opens up linearly in time with an aperture that's dictated by the maximal group velocity of your quasi-particle excitations. And in particular, the aperture is actually given by twice the group velocity, maximum group velocity, because to entangle or to correlate 2 points in space, you need a pair of quasi-particles to have originated from the midpoint. And so you only need the quasi-particle to travel half the distance between the 2 points to get them correlated. Okay. And by this mechanism, you expect then entanglement to build up in the system. So as quasi-particles move, they spread in pairs and they entangle space. And as a result, entanglement entropy, so the entropy of the reduced state of a subsystem A in this picture here, for instance, is supposed to grow linearly in time and to saturate around the time, which is related to the linear size of subsystem A divided by the velocity, the maximum group velocity of quasi-particles. Okay, so this picture here really finds in spin wave theory one very clear incarnation. And let me show it in the case of the long-range XX model. So this model here, if you treat it with spin wave theory, it has this dispersion relation here. It's explicitly written, but it's probably not so transparent. It involves the Fourier transform of the power law interactions among spins. But if you look at a small wave vector k, then you find that well, this system has a U1 symmetry, so you'd better have a Goldstone mode if you assume that it develops long-range order, that is a finite magnetization in the XY plane, and the Goldstone mode is there indeed. You have a gapless dispersion relation, which is power law in general, with a dynamical exponent z that is 1 if alpha is sufficiently large. So if alpha is larger than the number of dimensions of your system plus 2, then you have a simple sound-like mode a mode that has a sound-like structure at small wave vector. And the maximal group velocity is just the sound, the speed of sound, or the speed of spin waves at small wave vector, and then the velocity of aperture of the light cone would be twice this velocity here. And this is seen in practical spin wave calculations. You see this effect quite clearly. So you have a light cone effect for the correlations of the z spin components. With an aperture that's precisely given by the advertised law. Okay, so this is for alpha so large that you can actually consider the interaction to be nearest neighbor, but it holds up until alpha, so down to alpha equal to d plus 2. Now, if instead you look at more slowly decaying interactions in space, so alpha between d and d plus 2, then the z exponent becomes a continuous function of alpha and actually becomes smaller than 1. And by z is more than 1, having z is more than 1, what you get is that you have a concave dispersion relation. So no longer a linear relationship between omega, between frequency and wave vector. And that means that the maximal group velocity, that's the derivative fk equal to 0, can diverge. So in other words, you apparently lose the existence of a bound for the velocity at which signals can propagate in your system. So that would imply the breakdown of the light cone picture. But actually what you get, if you look at the correlations as they evolve in time, is some variation on the light cone picture. So what you get is, at least at short times, is what looks as a non-linear light cone. So you have correlations that appear to propagate no longer linearly in time, but somehow super linearly. So you have that distances are covered the distance that's covered by correlations at time t goes like t squared instead of going linear in t. So you can see a striking similarity between the picture of correlations in the space-time picture and the picture of the dispersion relation in the wave vector frequency space. So there is really a very nice correspondence, which you should take not so much to face value, because at long times the dynamics of the front of the correlation, so that is how the edge of the correlation function evolves in time, it's more complex than what appears at short times, and it's been investigated in details in this work. But let's say the fact that you can read out of the dynamics of correlations the nonlinear relationship between time and space is a fact, okay, as dictated by the low energy and long wavelength dispersion relation of excitations. But now, of course, there is more than just the small k the small k behavior to the dispersion relation of quasi-particle excitations. And where should you find more information in the light cone picture? Well, what I've discussed so far was just the dynamics, essentially, of the front of correlations. But you see that within the light cone, there's a lot of structure here, right? So there's lots of fringes. So how do what's in there? So what is it to be learned about elementary excitations by looking inside the light cone? It doesn't look very intuitive, what you could learn from here, but then spin wave theory tells you something that's quite illuminating. So it tells you that if you take the spin-spin correlation function and its Fourier transform at time t, so you get this object here. So it's the correlator between the Fourier transform of the magnetization profile at wave vector k and at wave vector minus k. So this object here evolves in time with a simple oscillating behavior, with a constant plus an oscillation at twice the frequency of quasi-particles, or the dispersion relation of quasi-particles at wave vector k. So that means that if you Fourier analyze the behavior of the spatial Fourier transform of the correlation function, you're going to get the dispersion relation. Okay. So in doing this, of course, you're exploiting the structure of the correlation function fully, you know, the front as well as what happens inside the light cone. So this insight from spin wave theory suggests to systematically go about and Fourier analyzing correlation light cones, what we like to call quench spectroscopy. So this is a way by exploiting by doing a quantum quench experiment or quantum quench calculation to try and reconstruct the dispersion relation of the elementary excitations in your system. And truth be told, this idea was kind of first, was already put forward first by the experiments before it was picked up in theory. And it's been already used in experiments in ultra-cold atoms or in superconducting circuits. And only more recently, we and other colleagues in Palaiseau have jumped more on the idea. But the idea remains very simple. And let me contrast it with the way in which you would reconstruct quasi-particle dispersion relations instead in the context of equilibrium quantum matter. So it's in condensed matter experiments. So let me go back to the first picture I gave you of, for studying quasi-particle excitations, which is the linear response theory paradigm. So there, what you measure, for instance, with neutron scattering, it's a spectral function. So in this case, it's a dynamical structure factor related to the imaginary part of the dynamical susceptibility. That is, something that gives you the rate at which energy is absorbed in your system at frequency omega and wave vector k. And more generally, the dynamical structure factor that you measure with neutron scattering is an example of a function of this kind. It's the temporal Fourier transform of a two-time correlation function at equilibrium. So it's a correlation function among operators at 2 times, evaluated on the equilibrium state of your system. We are in linear response theory, so everything should better be ascribed to equilibrium properties, in terms of the response of the system. And so I stress again, you have an equilibrium state and a 2-time correlation function. In quench spectroscopy, instead, what you would be measuring if you were studying the space-time dynamics of correlations and then take the Fourier transform in space and in time would be an object of this kind. It would be the temporal Fourier transform of the evolution of an equal time correlation function. So different from the 2-time correlation function entering in a spectral function. And this correlation function is evaluated not at equilibrium, otherwise it wouldn't evolve, but it has to be evaluated on a non-stationary state, which is the initial state. Okay. So going even more into the details of this difference, let me take the expression of the spectral function. So again, I'm back to the case of equilibrium studies of quasi-particles here, and let me rewrite, as it's customarily done, the spectral function as a double sum over eigenstates of the Hamiltonian. So by inserting, as I did at the beginning, the completeness relations of the eigens or the basis of eigenstates of the Hamiltonian, you get this expression, which is essentially tells you that this object, the spectral function, takes contributions in frequency as a sequence of delta peaks associated with transitions among eigenstates of the Hamiltonian. And these eigenstates must be connected by the OK operator that you are considering the 2-point correlation, the time correlation function of. And in particular, in this transition, the initial state, the departure state n, has to be populated by the equilibrium state. So there must be a finite probability for occupying it. Okay. Now, in quench spectroscopy, instead, the situation is rather different. So you can do the same analysis, just translate this expression into a sum over eigenstates of the Hamiltonian. And what you get is a seemingly similar, but deceivingly so expression. So again, the quench spectroscopy function is also a sum over pairs of eigenstates, over transitions between eigenstates of the Hamiltonian. But this transition now is not given by the OK operator, it's given by these two operators, OK, O minus K. And it's among states N and M, they need to be both present in the initial state. They need to have both finite overlap with the initial state, okay? So the initial state contains the two states that are connected by the transition. All right, so with this in mind, let's look at how, at a practical study of quench spectroscopy. Again, I'll look at the power law interacting XX model, initialized in its mean field ground state. And what I'll be looking at as OK operator is just the Fourier transform of the magnetization profile along Z. And so what I'm doing is just what I look at simply is the double Fourier transform space and time of the correlation function for the Z spin components. Okay, and then the spin wave result for this, I already stated it. It's going to state that this quantity here has a peak at frequency omega and frequency omega equal to 0, and a peak at frequency omega equals twice omega k. So how about a theory that's beyond linear spin wave? So how about a calculation that contains no linearity? Is this prediction going to stay? So let's look at a calculation then based on time-dependent variational Monte Carlo. It knows nothing about spin wave theory in principle, and that would give you, in terms of the space-time patterns of correlations, these pictures here. This is for a nearest neighbor interacting system, and this is for a dipolar interacting system. And these results are actually for 2 dimensions. I didn't comment that also the results that are presented before were for 2 dimensions for linear spin wave theory. Sorry about that, but okay. So you see that there is a very complex correlation pattern that emerges with lots of fringes. And again, it's difficult to make sense of it. But now if you take the Fourier transform in space and time, the situation looks a lot simpler. And what you observe is really a nice peak in frequency, wave vector frequency space. A ridge of peaks. This is for the nearest neighbor model, and this is for that dipolar interacting model. And what's shown here, it's just a possible. It's a typical trajectory one takes inside the Brillouin, 2-dimensional Brillouin zone of the system. Okay, and what's shown on top here of this picture is the spin wave prediction for, it's twice the spin wave frequency for the excitations. So I'd say that indeed the time-dependent variational Monte Carlo calculation confirms spin wave theory, the spin wave theory prediction fairly well. And so how does this go? I mean, why? So why should you to understand it, also to understand, let's say, retrospectively the spin wave prediction? Why are you expecting to see such a significant simplicity, in the structure of the correlation function once you take the double Fourier transform? But you can understand it again within spin wave theory by taking a linearized approach on your spin operators. So here the mean field state is along X. So that defines the quantization axis. That's the axis along which you should measure the spin deviation with respect to a perfect alignment in terms of bosonic population, okay? So that defines the relationship between the spin operators and the boson number. And then along the z-axis that you're looking at, you have instead transverse fluctuations. And so you're probing spin. So the z operator is related to a raising and lowering operator for bosons. And now in the quench spectroscopy function contains transitions within this linearized bosonic picture, transitions between states n and n that are connected by these operators, by operators that create pairs of or destroy pairs of quasi-particles B, and that also create and that transfer momenta from minus k to k, but don't create any net number of quasi-particles. And in a very rough way, you could associate processes that create pairs of quasi-particles to processes that relate states that differ in energy by twice omega k, whereas these processes here would not be associated to any net energy transfer if omega k is equal to minus omega k. So sorry, to omega of minus k, which is the case indeed in this case. Okay, so indeed, linear spin wave theory works very well, not only in predicting the form of the shape of the ridge of peaks, but it also predicts actually the sign of this spectral function fairly well. So it's positive at low energy, it becomes negative at higher energy. But there are significant corrections as well. So actually, the time-dependent variational Monte Carlo result is much richer. There are things that are completely missed by linear spin wave theory, but let's say the overall picture is correct. Okay, and this is true also even more so in the case of dipolar interactions. Okay, so this brings me to the end of the first part of my presentation, and the first partial outlook is that, well, linear spin wave theory for these gentle quenches starting from low energy, from mean field approximations of the ground state, works quantitatively. And in particular, it predicts that the dispersion relation of quasi-particles can be read out of the Fourier transform of the dynamics of correlation functions. And so, given the idea of quench spectroscopy, and actually quench spectroscopy is found to indeed work from calculations that go beyond spin wave theory, as the spin wave theory prediction is reconstructed, is by those calculations. So there's a cross check then among theories among approaches to conclude that indeed looking at the dynamics of space-time dynamics of correlations might be the way that that quantum simulator experiments have to reconstruct to do spectroscopy of elementary excitations of the systems that they implement. And of course, once I've stated this, one would immediately like to apply this approach to more general situations, such as, for instance, the situation in which you have exotic excitations, not necessarily quasi-particles. For instance, you could have fractionalized excitations. And I have an example thereof that I won't have time to discuss, but it could be in the overtime part or later on Gather.
Tommaso, you have a question, sorry.
Yes.
Yes, so I have a question.
Please.
Namely, so as you already said, it seems kind of to assume that the quasi-particles are sort of nice and non-interacting. But would this also work, let's say, in this real-time confinement setting? You know, where the kind of where there's also a clean system, but the light cone is not, let's say, completely clean in this sense.
Well, in that situation, so just to share it with people that might not be familiar with this. So I think what sorry, I only see your family name, Rakchiv, but so what he's referring to, I think, is a situation in which you take a system, for instance, an Ising model, and you prepare it into domain wall state, which is a state that is very far from the mean field ground state, or for the ground state, and from its mean field approximation. So in some sense, this situation, it goes away from the kind of setting in which I place myself. It's interesting in general to ask oneself how high in energy can you go with the initial state and still observe traces of the elementary excitations of your system, and possibly of linearized elementary excitations. So this is an excellent question that we don't have a general answer to. An answer that I can give in general is that if you start from a very high energy state, so what you will observe, going beyond the example of confinement that you gave. So suppose I take just a random initial state and I let it evolve and look at correlations that develop. Typically, the quasi-particles, even though you're very far from the low energy regime, quasi-particles excitations, if they exist in the dynamics, they will still reveal themselves because they are typically the fastest excitations that you have in the system, being free particles. The high energy excitations, you can often view them as being bound states of quasi-particles that are by definition slower. So the front of excitations will typically be given by quasi-particle excitations, by free quasi-particles. Now, if your initial state, going back to the confinement case, has little overlap with the low energy states of your that have linearized excitations, then you're not going to see much of this physics because you have kind of selected out that part of the spectrum from the initial state. Okay, that goes back to one of my first slides, where the initial state selects the kind of excited states that you want to see. Okay, so I don't know whether this answers your question. Okay, thank you. Anything else before I move on?
I would have a short question, more like a technical question. It was on slide 24, I guess.
Yes.
Yeah, this gamma k. First of all, is this correct that this sum only runs over J, or should it also run over I?
No, it runs only over J. I mean, sorry, I've written it kind of badly, but yeah. So you have a translational invariant system, so it's a sum over distances. So you can fix. It's not going to depend on Ri anyway. So the expression is correct, but it's kind of the I index is dumb. So you can just set Ri equal to 0. But then you have to exclude Rj. Sorry, this should be the sum over J not equal to I. So you have to exclude the singularity at R equal to 0, because there is no interaction of a spin with itself. So that term is not contained in the interaction in the coupling matrix.
And the second thing, this dispersion, is this an exact result, or is there some?
Yes. I mean, this is just it's just the Bogoliubov diagonalization that gives it to you. And then if you look at sufficiently small wave vector, this is of course just an asymptotic result, the power law dependence. And you can see that it fails at some point. You just flattens out.
Can I find the calculation for this in some of these references?
Yeah, like here. Yes, here it's fully given.
Okay, thank you very much.
Sure. Okay, Philippe has a question too. Please.
Yeah, hi there.
Hi.
So could you please comment on the essential difference between quasi-particle and elementary excitations?
In elementary, well, say quasi-particle excitations is just an instance elementary excitations. I mean, elementary, yeah, I don't know. I mean, it's difficult to say what, I mean, elementary would be like the lowest energy states, okay? In that sense, they're elementary. Oftentimes, high energy states being sort of compound objects of lower energy excitations. So in the picture of quasi-particles, then what's elementary is when you add one quasi-particle at a time, and then if you have more than one quasi-particle at a time, you may have two of them that interact and then maybe form a bound state, or in any case show nonlinearities, and then it's not elementary anymore. Okay.
Mm-hmm. Yeah. So as far as my knowledge goes, I think about quasi-particles as having not real energy, but complex energy, imaginary energy.
Yeah, well, if they decay, yes. So here, yeah, this is a way to think about nonlinearities as a decay effect on quasi-particles, and that's perfectly right. So that means that you have that in these dispersion relations that I gave you. I mean, this is kind of, if you wish, it's expressed indirectly by the fact that there are widths to the in frequency to these peaks. Okay, that means that there is a finite lifetime of quasi-particles. And well, in the picture, it's an effective way to think about it. Say the full picture would be that you introduce nonlinearities, and then yeah, so you have interaction phenomena that let quasi-particles decay either. So let's say 2 into 1. There are different phenomena that can arise depending on the model, and they can be accounted for again at the level of nonlinear spin wave theory, but it's a different story. Okay. But okay, so a way to, you probably there would be, I don't know, there could be a way to incorporate the effect that you're talking about by adding an imaginary term, effective imaginary term to the frequencies. I haven't thought about it, and I don't know whether anyone has ever done it, but it's probably interesting to think about it.
Yeah. Okay. I just wanted to get clear about this, because normally people use these two terms, elementary excitations and quasi-particles, interchangeably.
Yeah.
But I guess they are quite different, because the elementary excitations, they do not decay, right? They have real energy.
Yeah, I mean, see, I'm not using them interchangeably in the sense that there are. I mean, depends on what your quasi-particles, what the definition of quasi-particle is. So there are situations in which quasi-particles are created, in fact, in pairs. Sorry, in the excitations you have pairs of quasi-particles always, because you have objects that fractionalize into pairs, and so so in that case, yeah, I don't know. I mean, it's still still a quasi-particle picture, but not as simple as the one that is offered by spin wave theory.
Okay. Thank you.
Thank you. Anything more? All right, so if that's not the case, I think in the interest of time, so let me skip the part, well, as I advertised already, on disorder. So, well, maybe I just can say it in 2 words. So all I've discussed so far was for translational invariant systems, but spin wave theory doesn't fear the presence of disorder. In fact, one of the organizers of the school, Nicolas, knows this very well. He's applied spin wave theory to disordered systems very successfully. So you can apply it to disordered systems, and I won't go into the details of the system that we looked at, but the idea is just that you can rephrase everything that I've discussed. So the linearization of the Hamiltonian in terms of bosonic operators, and then the Bogoliubov diagonalization in the case of systems that have no spatial symmetry at all. You just need to have a generalized Bogoliubov transformation in terms of eigenmodes that don't have obvious quantum numbers like a wave vector, but otherwise, eigenmodes, Bogoliubov eigenmodes. And an important message that comes from studies like this is that even though the ground state of your system may be trivial as to be describable by a spin wave theory, by mean field description plus small quantum fluctuations, the excitations may be highly non-trivial. They could be Anderson localized by disorder, or they could be even fractal, even multifractal, and the dynamics that's going to ensue is extremely rich, and that's this is the content of this study that I'm just advertising shortly, and I can again discuss this in more details if you're interested offline. Let me go to the final part of my presentation instead, which concerns going finally beyond the picture of quasi-particle excitations. So maybe this is like a more educated answer to Felipe's question. So do elementary excitations correspond to quasi-particles? Well, yes, but let's say in the thermodynamic limit. On finite size systems, which are the ones, by the way, of interest for quantum simulator experiments, there is more life than quasi-particles. Okay, and this is a message that comes from the most recent work that we've done. Again, it's focusing on finite size dynamics. Let me go back once again to the assumptions of spin wave theory, and so in general to quasi-particle pictures of excitations. So in spin wave theory, you assume again that your state evolved in time preserves the initial order that you imposed on it with the initial state. In terms of a collective spin operator, the sum of all the spins, that implies that the average value of the collective spin, if the initial state was sufficiently uniform, the average value of the collective spin remains finite, okay, at all times. Now, the fact that under the dynamics, the system preserves a finite value for an order parameter, it's actually the definition of spontaneous symmetry breaking, as we learn it in our classes about critical phenomena. Namely, spontaneous symmetry breaking, in its most fundamental definition is that you look at the time evolution of the order parameter of your system once you have imposed it on your system, by first taking the thermodynamic limit on your system and then taking the infinite time limit in this specific order. Otherwise things don't work. And if you have a non-zero value for this expectation value, then you have spontaneous symmetry breaking. So that means that spontaneous symmetry breaking is the underlying assumption behind spin wave theory. Okay, I just already said this, but let me state it again more formally. Now, if you have a finite size system instead, well, things get more complicated. Well, they can still, life still can be easy for spin wave theory if the time over which the order parameter decays is very long. So stated otherwise, let me go back one step. So if you take these limits in reverse order, you're going to get always zero. Okay, so there is always relaxation of the order parameter any finite size system, but it depends how slow the relaxation is going to be, in terms of the applicability of theories that assume that relaxation doesn't happen. If you're looking at the discrete symmetry breaking, like, sorry, I have the phone ringing. Sorry about that, just a second. If you take you have a discrete Z2 symmetry, oh boy, just a second again. And so in this case, the relaxation dynamics of the order parameter can be thought of as being as the physics of a double well. So you have two states that are connected by Z2 symmetry. You prepare your system in one, and then you have to tunnel into the other one to restore the symmetry. And this is done. It's a tunneling phenomenon across a barrier that's typically extensive in energy, and so it's a phenomenon that takes an exponentially long time. So with a discrete Z2 symmetry, I think you are in good shape, to apply spin wave theory even to finite size systems, and things are not. So you won't see the effect of finite size if you look at sufficiently large systems. On the other hand, actually all of the systems that I've discussed today have a continuous U1 symmetry. And in that case, well, the energy landscape in which the order parameter is defined is rather a Mexican hat. And there, there's no energy barrier for the order parameter to spread around and restore the symmetry. And the time it takes for the order parameter to decay, it's typically linear in the system size instead. And you can just, take the argument for this estimate by imagining the dynamics that has to destroy an order parameter, and that is just, that is locally evolving the order parameter in steps. It's transferring quanta of angular momentum, let's say, to the collective spin at every time step, and so it takes a time that's linear in the system size if the order parameter was macroscopic in the first place. Okay, so in terms of how this dynamics of your parameters translates is related to the excitation spectrum, which is in the end our object of interest in this presentation. You can say that the discrete Z2 symmetry that's restored over an exponentially long time is actually related to the existence of a low-line doublet in the spectrum of two states that are actually symmetric and antisymmetric superposition of the two states with opposite order parameter. And this the splitting among these two states which is the tunnel splitting of this picture, is exponentially small in system size. Okay. On the converse, if you're looking at the continuous U1 symmetry, well, in that case, the quantum dynamics that restores the order parameter symmetry can be thought of in its minimal with a minimal model in terms of the dynamics of a planar rotor. That's actually the simplest model you can write in the spirit, if you wish, of a Landau kind of theory, which has an extensive energy and it has U1 symmetry. So the U1 symmetry is given by the fact that you take Z, also a Z2 symmetry, which is not written here, but so you assume to have also spin reversal symmetry along Z. And so the Hamiltonian is of this planar rotor model is quadratic in the collective spin along Z, and it has a moment of inertia which goes linearly with the system size in such a way as to have an extensive Hamiltonian. Okay, and this kind of Hamiltonian then would suggest that the low energy part of the spectrum of a system with continuous U1 symmetry on a finite size has a set of states that are the eigenstates of this rotor Hamiltonian, with separation that goes like 1 over the system size. Now, these states are necessarily lower in energy than the quasi-particle excitations that I've been predicating so far, because the quasi-particle excitations actually have an energy spacing that typically goes like the inverse of the linear size of your system. So if you're in dimension higher than 1, then this spacing is parametrically larger than this spacing here. So as the system size becomes larger, these states will occupy the low energy part of the spectrum. Okay. All right. So the idea that there is a so-called tower of states associated with the emergent dynamics of a planar rotor that describes the low energy part of the spectrum was put forward by Anderson a long time ago, soon 70 years ago. And well, it's called the Anderson Tower of States for this reason. Every time I think about a tower, being Italian and coming from Tuscany, also I think about the Pisa Tower. So here it is, and so again, this planar rotor Hamiltonian should be the description of the low energy part of the spectrum of this of this Hamiltonian. And sorry, let me state once again that all that we've described so far are the black lines here in the spectrum. So this red part is new, is unknown to spin wave theory, because this part of the spectrum is supposed to collapse to zero energy in the thermodynamic limit and to not be observable. But I'm looking at finite size systems, so off we go. And now, looking at a finite size, at a concrete realization of this tower of states, let's look at the power law interacting XY model, XX model. And here are spectra for the two-dimensional XX model in 2 dimensions on a small system that's as small as it gets when you want to fully diagonalize it, for nearest neighbor interactions and for dipolar interactions. And here the energies are organized as a function of JZ squared, which is a good quantum number, and it's also the quantum number for eigenenergies of the planar rotor Hamiltonian. And here, don't care about the size of the symbols or this orange line. They don't matter so much. All you have to look at is the position of the dots, and you can see that there is clearly a low line part of the spectrum that has energy growing linearly in JZ squared in both cases. So there is a tower of state, and then there are states up above instead that have a different that follow a different life. Now, to understand these low energy states, you can use this picture of U1 symmetry breaking, or even more simply, you can think of a spin boson transformation that now it's exact, it's not linearized, and it's a mapping between the spin 1/2 spins that define the model of interest and hardcore bosons. So it's an instance of Allstein-Primakov transformation, but I'm taking here hardcore bosons, so the transformation is exact. It looks deceivingly linear. Sorry, here there's a typo. It should be BI dagger BJ. Anyway, this Hamiltonian is for interacting particles because they have a hardcore constraint on site. But in any instance, it's a model of long-range hopping bosons, which in 2 dimensions or in 1 dimension for sufficiently slowly decaying interactions, like to Bose-Einstein condense in their ground state. And the JZ label here maps onto the number of bosons in this model. So it's number of bosons minus n/2. And so these different states, as well as these ones here, are just ground states of long-range hopping hardcore bosons at different fillings of the lattice. Okay, so clearly they are special states in the spectrum, being ground states of bosonic Hamiltonians or of spin Hamiltonians at fixed magnetization along Z. And I'd like to make a further statement about these states. You have heard already in Anusha Chandran's lectures and probably in other lectures as well, and you'll hear it again, I presume, during the school, that there's such a thing as quantum scars. Even in models that have no specific form of integrability, that only conserve a small number of quantities, there can be special states in the spectrum that have atypical features. Well, I'd like to claim that the Anderson tower of states is a very simple, in fact, example of a tower of quantum scar states, and you can see it again, with this scheme that's just a sketch of the picture, of the real picture you've seen before. So either you can think of your system as a spin model or a bosonic model. It has this structure of eigenstates as a function of energy. It has of energy and JZ, or number of bosons. It has this low-lying tower of states. There are actually extensive in number. They're just n+1. You can count them. It's very, very easy. They come into pairs of degenerate states because there is a particle Hall symmetry in the bosonic model, or a Z2 inversion symmetry in the spin model that makes JZ and minus JZ having the same the same structure. So here, or in other words, I could just take negative values of JZ and you would see the same picture exactly. And now what's important is that these line, sorry, that the states that are not in this line, let's say states that are inside the high energy part of the spectrum, they have volume law entanglement, as you know, as generic high energy states should do. But these states here can climb up in energy all the way up to energies that are associated with typical states with volume law entanglement. Yet these states are ground states of a bosonic Hamiltonian or spin Hamiltonian at fixed magnetization. And so they are error law entangled states, as typically is observed in bosonic ground states, and in particular for this system. Okay. All right. So okay. So much for the general description of the Anderson-Tauro states. So let's see how they manifest in the dynamics. So the manifestation in the dynamics is going to be, in terms of the evolution of the order parameter, as advertised. They should be describing. Let's go back to this picture. They should be describing the dynamics of relaxation of the order parameter in a U1 symmetric system. So let's look at a practical calculation of such a phenomenon, which has to be beyond spin wave theory. This is a time-dependent variational Monte Carlo calculation. And it's done, in this case, it's done on a one-dimensional realization of the power law interacting XX model with alpha equals to 2. It's a situation in which even in one dimension you have a long-range ordered state. And this is the order parameter as it decays in time. It has lots of revivals, in fact, but the time here is rescaled by the size of the system in such a way that system that twice the size, it's is rescaled by the factor of 2 with respect to the system of size n. And you see that from the collapse or partial collapse of these different curves, you already see that there is a characteristic time scale that goes linearly with n, and that's what I advertised, what I announced at the beginning. And now, looking at the time-dependent behavior of the order parameter in the system, the first thing that comes to mind with this quench spectroscopy idea is to take the Fourier transform in time, sorry. And this Fourier transform is very illuminating. It contains peaks that are equally spaced, and they are with a spacing that actually goes like the inverse of the size of the system, as you would expect from a dynamics that instead has a characteristic time scale that goes linearly with n. And in fact, you can precisely predict the position of these peaks by thinking a bit for a moment of what the Fourier transform of this object should be in this quench spectroscopy picture. So the Fourier transform of J, of the time dependence of Jx should contain transitions between eigenstates of the Hamiltonian that are connected by the Jx operator, which is J plus J minus. So it's raising and lowering operators for the collective spin. Now, if M and N are states of the Anderson tower, that means states that have a well-defined JZ. So these transitions here are between states that differ by a unit of JZ. So the frequencies that are associated to them should be differences between the tower of state energy at JZ plus or minus 1 and the tower of state energy at JZ. And these frequencies here are just equally, they grow linearly with the JZ index. So they give an equally spaced path, an equally spaced frequency comb, with what in atomic physics would be called a Lande rule. Okay, so very simple structure of the spectrum that you can reconstruct spectroscopically by taking the but a la quench spectroscopy. Okay, and all right, so I'm getting close to my the end. So a final remark is that the tower of states being an instance of quantum scarce, it actually gives rise to an interesting dynamics because the initial state is strongly overlapping with the Anderson tower state. So the dynamics ensuing the preparation of the state in the mean field ground state, is a so-called quantum scarred dynamics. It is dominated by the tower of states. And you can see here that this is the overlap of the excited states of your Hamiltonian. In this case, it's for a two-dimensional system for different values of alpha as a function of Jz. And this is the Anderson tower of states, and these are the low line. The orange ones are the higher energy states. And you clearly see that the initial state overlaps primarily with the tower of states, and also that the tower of states has a very large total angular momentum. It has by far, so the blue points have by far the largest values of J squared, which is maximized in the initial state by construction. So hence the very strong overlap. So let me rush to the last aspects here, but just saying that the quantum scarred dynamics of the collective spin in the simple parallel interacting XX model features something that's very interesting, which is a particular way of developing entanglement, which is highly non-typical. And you can understand this by changing language for a moment and using the quantum optics language. So in quantum optics, these states for spins are very well known in the context of spin ensembles interacting with light. And this is called a coherent spin state. It's just a state polarized along X. And this Hamiltonian, the planar rotor Hamiltonian, is also very well known. It has a different name. It's called the one-axis twisting Hamiltonian, just a name. But then if you look into the quantum optics literature of a combination of a coherent spin state that's evolved with the one-axis twisting Hamiltonian, what you get is a very interesting form of evolved states that are called spin squeeze states, with spin squeezing that appears at a time optimally at a time that scales with system size in this way. What's spin squeezing? Well, spin squeezing is a reduction of the fluctuations of the collective spin along a specific axis in space. So if you can represent the state of the collective spin on a block sphere, if its length is conserved, as it is in the case of the one-axis twisting dynamics, and in the initial state, the coherent spin state, the spin actually has to be thought of as being delocalized over an uncertainty region. So it's polarized along X, which is the axis that's coming out of the plane, with uncertainties that are uniform along Y. There are symmetric between Y and Z. Y and Z. And then as time evolves, in fact, the uncertainty region is elongated in one direction, but it's stretched in transverse one. And one then defines a spin squeezing parameter, which is the ratio between the variance of the component that has minimal fluctuations transverse to the order to the x-axis, and the polarization along the x-axis. Okay, and this squeezing parameter, when it's smaller than 1, it tells you that there is squeezing. It tells you that there is entanglement in the system, that the state is not separable. This parameter can become as small as you like at this optimal time if you scale the system up. And actually, it's squeezing is known to be the most fundamental resource for quantum enhanced metrology. So that means that the dynamics or the squeezing dynamics has also, not only a fundamental interest, but also potentially, some application, some interest in applications. And to wrap everything up, let me show the dynamics of spin squeezing in the parallel interacting XX model. This is the case of one dimension for low value of alpha, is alpha equal to 1 in this case. And there you observe that indeed the squeezing builds up, and it builds up exactly with the same predictions as you would have for the one-axis twisting Hamiltonian. That is, the description of the low energy physics given by the Anderson tower of states is in fact faithful to the dynamics of the collective spin. And whereas, well, this is not the case if alpha is sufficiently large, and we have an argument, you know, as of why alpha should be smaller than some combination, some fraction of the dimensional spatial dimensions of the system for the one-axis twisting picture to stay in place. Okay, I think I went nearly, I mean, actually, I'm nearly over time. So let me, before concluding, let me acknowledge my collaborators throughout these studies about quantum dynamics. Irene Frérot, who's now at ICFO in Barcelona and soon will be in Grenoble. Pierre Aldesi, who's in Innsbruck, Raphael Menu in Saarbrücken, and the people that are still in Lyon, Tommaso Comparina and Fabio Mezzacapo, who actually are even in the audience, or at least they were before I noticed them. And the conclusions really to go fast over them is that hope I gave you the message that joining different methods that are all uncontrolled in their own ways is a good strategy to get a coherent picture of quantum many-body dynamics, you know, in the absence of a silver bullet method that would tell you the truth in a controlled way, which is typically the case. Moreover, quantum quench dynamics that you could explore with quantum simulators provides a fresh look, I'd say, into excitations, both theoretically as well as experimentally, hopefully. And also that there is a, I mean, in particular, the fresh look that I see here is the existence of a duality to Fourier transform between the quasi-particle dispersion relation and the space-time evolution of correlations. And moreover, you can go beyond quasi-particle pictures, the quasi-particle picture, and see excitations that are below even the quasi-particle ones in mesoscopic systems, that is the Anderson Tower of States, which I think have never been observed in any experiment. So, I mean, I think really this is the setting where this could be observed for the first time. And with this, let me thank you all for your attention, and sorry for going slightly over time.
Thank you, Tommaso. So it was very good, and we have a little bit of time if there is one or two questions. Yes, there is a question by, I don't know. So you can speak. No, there was a question, but it's gone. Okay.
I have a question. Can I?
Please.
Yes. So, Tommaso, I was a bit confused because I always thought that scars are supposed to be unprotected by symmetry. Yeah, that's why they are strange and exotic. Yes. While here you are showing us just different symmetry sectors, and in each symmetry sector you have its own ground state. So they are protected by symmetry. So are you sure you can call them scars?
I mean, this is a great point. Actually, they are protected by symmetry, but not quite. I mean, because they say the Tower of State Hamiltonian is actually, it's a caricature of the low energy sector. I mean, this assumes more symmetry than there really are.
Wait, does the Hamiltonian conserve JZ?
It does, but this Hamiltonian conserves more than JZ. It conserves J squared to the total spin squared, which is not conserved by the Hamiltonian. So to have a perfect quantum scar picture, you would need to have conservation of J squared it would need to have the Hamiltonian commute with the collective spin squared. And which this thing does not. So in that case, you would have an integrable model. I mean, it would be.
Wait a second. If the Hamiltonian commutes with JZ, then it also commutes with JZ squared.
No, you just have, because you, so it doesn't commute with the total spin squared. It doesn't commute with obviously it doesn't commute with the x squared, jx squared and jy squared.
No, but here we have jz squared, right? We don't have j.
No, this Hamiltonian does, but this Hamiltonian, the microscopic one, doesn't I mean, it doesn't commute with jx squared and jy squared.
But do we need jx squared and jy squared?
We do for the Anderson tower of states to be the truth, to be to be you know, an exact description of the low energy eigenstates. So these eigenstates have energies that are, you know, the energy that depends on jz squared linearly, as shown here, but they don't have a well-defined j total squared, which is seen from this picture. You see that the j total squared is near to maximum, but not quite. I mean, it deviates a little bit. So which means that yeah. That means that the actual eigenstates of the Hamiltonian are superpositions of a few states with different with well-defined j squared. Which gives way to leakage out of the quantum scar manifold in the dynamics, if you wish.
Okay, thanks.
Okay. I have also a little question about this. So you show, when you show in the Fourier space the peaks, there was a finite size. So we saw that it was
here.
Yes, this one. So increasing the size, they are going away because they are finite size effect.
They are. So why do they go away? Actually, they go away because they comes from the excitation content of the initial state. So looking at higher frequencies, that means that you are looking at transitions between, let's say, the ground state of the tower of states and a state that has higher and higher jz. Now, the initial state, it's a coherent spin state. It has a Gaussian distribution of I haven't said this, but it has a Gaussian distribution of possible values of jz. It has a jz not well defined, but Gaussian fluctuations with the width of the Gaussian that goes like square root of the particle of the number of spins. So this thing here is going to, we haven't studied so much in details, but I think it decays like one over the square root of the frequency.
Okay.
Because
this was also interesting. No, I was asking why they are going down when you increase the system size. Green is smaller than blue.
Because you are. I mean, I think because you actually there are other states beyond the tower of states that are entering into the game. So the picture is not. So the description in terms of just planar rotor states is less and less accurate. In other words, yeah. So in this picture here. Here the initial state is overlapping more and more with the black states that are coming down in energy as well.
Okay. So Tommaso, we have to stop because now there is Mari Carmen. So absolutely. I stopped the recording. Thank you very much.
Thank you.
For all the students, if they have questions, and also maybe if you can put, for example, your slides, or if you have materials, absolutely, you can add on the Slack. Okay. So let's thank again Tommaso.
Thank you.
And then I stop recording. Okay.